Right, so what we talked about the wave properties of electromagnetic radiation. And as I say, until the 1920s, people thought that was the way you treated electromagnetic radiation. But with the development of quantum theory, people like Einstein and Planck showed that you also need to treat electromagnetic radiation as a particle or a photon. Because there are certain experiments where you can't explain, you hit electromagnetic radiation on a certain material, and what happens can't be explained by a wave. You may have in school, if you did physics, you may have done the photoelectric effect where you knock electrons off a certain material. And you can't explain that in terms of a wave. It's the electromagnetic radiation is behaving like a particle. It's physically knocking the electron out. So to understand that, you have to also say that in certain cases, electromagnetic radiation behaves as a photon. And Planck was the main proponent of that, and he proposed this famous equation, which I assume you've all seen, is that E is equal to h nu, where nu we've already defined as the frequency of the electromagnetic radiation, and h is Planck's constant, 6.626 by 10 to the minus 34 joules a second. Okay, so you should all, if you don't know it already, you should all be able to remember this fundamental equation. So I've given Planck's constant there. So now you need to also be able to, especially for spectroscopy, we'll find a different form of spectroscopy. Sometimes we refer to the wavelength, sometimes we refer to the frequency, sometimes we refer to something else called the wave number. So you need to be able to know what these are and how to change between them. All spectroscopists have to be able to do this without thinking, really. So the first equation here you should remember is E is equal to h nu, and then we know that C is equal to lambda times nu, so you know that nu is equal to C over lambda. So therefore you can move on to this one here, that E is equal to hc over lambda. So again, if you haven't seen this before, you're not familiar with it, you need to be. So the energy of a photon wave is directly proportional to frequency. Okay, so that should be obvious from this equation here. E is equal to h nu, E is proportional to frequency, and h, Planck's constant, is a proportionality constant. And the energy of the photon is inversely proportional to the wavelength. And if you think back at the slide we had with the electromagnetic radiation spread out, the longer the wavelength, then the lower the energy. And this comes from this relationship here. You can see that E is proportional to 1 over the wave. Okay, another way is you define it in a joule, is the SI unit of energy. So you can have joules per fundamental particle, or you can have, sometimes we convert it, a more common way of using is kilojoules, where kilos 10 to the 3 joules per mole minus 1, express it in per mole. So you need to be able to convert energy between these different forms. And another way you'll often find in spectroscopy is this definition here. Here we have hc over lambda, and here you have hc into 1 over lambda. So that's the inverse of the wavelength, and that's often denoted here by this nu bar. So you have something like a nu, and you have a bar over it, and that's often called the wave number. And as I say here, in SI units, for length, we use meters. So therefore, nu bar 1 over the wavelength should be meters minus 1. But you'll find in a lot of spectroscopy, it's defined as centimeters minus 1. Especially when we move on to infrared spectroscopy. If you see an infrared spectrum, it's usually defined in centimeters minus 1. And usually you might be wondering, why do they use different units for different spectroscopies? And sometimes it's easier to understand. The way the region of infrared has nice numbers, if you like, in centimeters -1. So it's easy to follow variations in it. Whereas in something like UV spectroscopy, sometimes they talk about nanometers. And again, that's because it gives you nice numbers. You don't want lots of exponential numbers because it's difficult to understand it. But the wave number is meters -1, but nu in, usually and that in centimeters. And again, sometimes students have a lot of trouble converting, say from nu meters -1 to centimeters -1. What you got to remember here is, you have 100 centimeters in a meter. Most people get that, but then it's going the other way around that people find difficult. And you have to think of the number of waves in a given distance. So here we have a meter per meter. So the number of waves in that is going to be a lot bigger than the number of waves in a centimeter per centimeter. So there's 100 times more waves, if you like, in a meter than there is in a centimeter. Okay. So it's one way of thinking that. Usually people tend to mess that up.